we have algorithm and we want to know how this algorithm will behave when the input size increases. So focus on this. Asymptotic notation purpose is for the large input values, means for the input values which are greater than n0, and suppose n0 is the, like, suppose it's a big value. We are not going to consider small values 1 2 3, no, for large values, for the values which are at least greater than n0. For large values we want to see how our algorithm going to perform in three cases. When our algorithm performed best, it means it ran fast, took less time, less possible time, and opposite of this is worst, when it took a lot of time, the slowest possible time. So this is the time an algorithm can take when, guys, focus, when n is greater than no. No is key when we have large values. In that case, asymptotic notation. Suppose I have a notebook with n number of pages. Let us take an example of this notebook. I have n number of pages in this notebook. I am going to search name which is written on one page. So I will start from the page number 1. There could be case I can find name on first page. This is the best case. I have to do only one iteration. I have to look into only one page. I don't have to go through all of the pages. But worst case is when the name is written at the last page. When name is written at the last page, suppose I am looking for name Nita and it is on the last page, I will go through all the pages and then I will found it on the last, which is n. So this is the worst case for searching. What is the third case? Third case is maybe the name is written in between on any page, maybe this. So this is the average case. So let us see these three cases. Let's talk about the worst case. The maximum time an algorithm takes. The maximum time. In this case, the maximum time to search the name is n. N is the maximum. So the worst case is represented by big O notation. Big O notation, and this is the most commonly asked notation in interview. The interview will only ask you the worst case scenario for an algorithm. So what are the worst case possible? When the element is at last index, at n index, or maybe element is not there in the iteration. So in these cases we have to iterate through whole of the array. So this becomes the worst case and we have to check all the n iterations. It means no matter what, it will not be slower than this. Algorithm slowest performance time is this, and opposite of this is best case. In best case, element is at index 0. Example, we have found name Nita at index 1. The time complexity or time will be 1 unit. So it means our loop stops immediately. We don't have to go through whole of the array. Our array stops immediately after finding name or value at first index, and this is the best case possible. Means at best algorithm can be this fast. This is the most fast time complexity possible for the algorithm, and this is the most slow time complexity for the algorithm. So both are opposite, and in between comes the average case. So if you find the name or value at anywhere in between both of the lower or higher limit, if you find any value between the lower and higher value which is in between anywhere in the notebook or in the array, so that is the average case. I'm trying to make you visualize the cases. Least time will be big omega, which is the fastest, and the maximum time it can or time complexity it can take is big O, which is the worst case when our data is at like when we have to iterate through all of the data, and in between we have big theta. So whenever in interviewer says calculate the time complexity, we have to calculate the maximum time an algorithm will take, like for the worst case big O. This diagram is especially for the worst case. So suppose these are like 1 2 3 n items. I am taking n O. This is a very large number, suppose, and this is the upper bound. Means this is the worst time possible this algorithm can take. Okay, so irrespective of n is 0, n 0 plus 1, now like so on, n 0 plus 10. For all cases when n0 is greater than or equal to n, like n is greater than or equivalent to n, in all cases for this n, this is going to be the graph. For this is going to be graph, this is going to be the graph. In any n case we are not going to cross this line, we are going to be inside here. So basically our fn will always be inside the upper bound or under the upper bound or equivalent to the upper bound. Upper bound we are writing it as c dot gn. So the value of the upper bound we write as c dot gn, and our function will always be under the cgn or equivalent to the cgn. So let us write this function here. Our function n will always be lesser than or equivalent to the cgn. So this gn is basically, you can assume when we were calculating the time complexities, so there were some values like n square we were computing after dropping the constants. So these values are actually cgn, and these are the constants which we were dropping. The time complexity of our algorithm will always be under this upper bound. So this is the upper bound, and also this will be greater than 0 or equivalent to 0. So in best case for big omega, our algorithm's time complexity will never go below this limit. This is the best time or best speed possible. Below this it can't go. It will be always greater or equivalent to what, this big, this cgn, this value, what our function will always be greater. And if you see, this is exactly opposite of the above, and of course our cgn will be greater or equal to the 0 because this is the lower value. Our fn can match it or will stay above it, but will never go down this value. And the third case, I guess you are good to go to calculate